In this example of an axially loaded system, meaning that we have this bar here, we got a load applied to that bar, and we have a rod that is providing the primary resistance to the applied force. This rod is the one that is axially loaded. This bar, ABCD, is really a beam, and it's to be regarded as rigid, so we will not include the relative deformations of this or the performance or behavior of this bar in the system. Now, that it's a statically determinate system would mean that in reality it won't change any of the force related aspects of the system. And when we get into indeterminate systems, we'll talk about how that might change things, whether the bar is rigid or flexible. We're also asked to find not only the force that causes the aluminum rod to yield, but also to find the corresponding displacement at that instant. Notice that we've got the 12 inches between A to B, 12 inches between B to C, and 6 inches from C to D. And we have rewritten the pertinent parameters both material-wise and geometrically for this member: the length, the area, the yield stress, and the modulus elasticity. Again, where the conditions under which the analysis are being conducted is what load can be applied at D if the stress of the aluminum rod is to be no more than its yield stress. We have just specified that this condition is that sigma in the aluminum is equal to its yield value of 60 KSI. That's our conditions of analysis. So I already got started with the equilibrium. Here I've got the free body diagram of the beam. Notice that I've got the two reactions, AX and AY, the applied load P, and then it's relatively intuitive that if we're, in this case, trying to pull down the supports over here in this bar, it wants to rotate in a global clockwise fashion, which would want to extend this aluminum rod. That means it's going to put the rod into tension. Right, so we see this B sub y, and then I've chosen to also show the free body diagram of the aluminum bar. We've got an axial force, NAL, and notice that, hey, these two have got to be the same. They represent the same thing, and so NAL is equal to BY. Why this additional overburden to do it that way? Because I'm preparing the way for the similar looking system that now is going to be an indeterminate structure, and this kind of notation will be helpful later on. Probably not necessary right at this stage. So since we're doing this analysis under the condition that NAL is a specific condition, that is, the system is yielded, so we'll take the yield stress times the cross-sectional area for the aluminum to find that. So let's get that number. We've got 60 KSI times the cross-sectional area of 0.8 square inches. Kips per square inch times square inches will give us a force in kips, and 60 times 0.8 is going to be, of course, 48 kips. That's just the force that is in this aluminum rod. Now, the equilibrium conditions are what will then allow us to find out what the value of P is that corresponds to this situation. Under the special condition, I'll call that P sub y for yield. And now we have, by taking sum of moments about A, let's go clockwise positive, that we've got 12 inches times this upward force on the bar. Not the downwards force on the member, but the upwards force on the bar. That's the equilibrium that we're associated with here, is the bar itself. And that value is 48 kips. We found, so 48 kips times our 12 inches for the moment arm. And that would be going opposite of our sign convention, so minus, plus then P sub y times its moment arm of 12 plus 6, or 30 inches. Only forces in that equation, so set that equal to 0, and we will find then that our P sub y will be equal, once we solve all that out, to 19.2 kips, acting, of course, downwards. If the material has the same compressive yield stress as the tensile yield stress, then we could switch that force around and it would be exactly the same answer, so long as we're not including the effect of buckling once we put that rod into compression. When we get into the displacement side of things, we need to create a displacement diagram. So our bar is rigid ABCD, and after it responds to the load, it's going to pivot about point A. Remember, small deflection theory or first order theory, we're going to ignore that that's actually an arc, making a small error, but the differences will be so small and minor that it won't have any practical significance to what we're trying to accomplish. And delta D is out there now. The flexibility or stiffness of the system is all coming from what's attached at point B. So there's our delta B, and by similar triangles then we get that delta D is going to be much larger than delta B by directly the ratio of that total distance of 30 inches. Right? Hey, that's the same as the moment arm. You bet. These are directly related. 30 over 12 times delta B. Right? And so I'm going to guess here 30 over 12 is probably 2.5. But, indeed, it would be. Right? 6 would go into 12 2 times. 6 would go into 30 5 times. 5 over 2 is 2.5. So that's your displacement relationship. Now that's the displacement of point B, but that's directly associated with the elongation of this aluminum rod. And since the top end doesn't move, then the displacement at B is going to be entirely just that axial extension. And so delta B equals little delta of the aluminum, and that would be NL over AE of the aluminum. We already know the stress because we had set that as a condition of analysis. So that would be 60 KSI for the stress. That's this first part. The length is 10 inches, and the modulus of elasticity is 10,600 KSI for this particular type of aluminum. Not all aluminums are the same. KSI's cancel out. 600 over 10,600 will be 0.0567 inches, of course acting downwards for delta B. And then we substitute that back in for delta D, which equals 2.5 times whatever delta B is, and 2.5 times 0.0567 will be 0.1415 inches, acting, of course, downwards. That corresponds to the yielding condition, so I like to add that subscript Y in there someplace to make it clear what's going on, and there's your answer.